So today we'll be focusing on sketching the root locus. So this usually is the fun lecture because it's about sketching things, and we will be observing the locations, so the movement of the poles, in order to see how the system can be stable, or what happens when you change a factor k, and how the stability of the system could change because of that. And we'll do all of that by sketching the root locus of a given system. And to help with to help with determining the stability, we can also use a Routh-Hurwitz criteria, which is essentially a shortcut to find out the location of the poles. So this is essentially, the second part is essentially a shortcut to find out where the poles of a high order system are located. Most of our lecture time will be dedicated towards sketching of the root locus, and we need to talk about several rules that we need to follow. So as long as you're following those rules, you will be able to sketch the correct root locus for a given transfer function. Let's talk about the root locus. So that's our topic today, sketching the root locus diagrams. It's all about sketching things. Now consider the feedback system that is shown on the left. What you have, everything is represented in the Laplace domain. You have x of s as the input, h of s is your transfer function in the forward path, y of s is the output, which is being fed back through these feedback dynamics kg of s, and a negative feedback is provided with x of s back into the system. Let's see here what happened. Okay. Are we back? Okay. So we have on the left a feedback system whose closed loop transfer function is determined as t of s, which is y divided by cap x, and these are all represented in the Laplace domain, forward divided by 1 plus product. So forward we have got h of s, and divided by 1 plus product we have got the multiplication of kg of s and h of s again, right? So we saw techniques how to derive the closed loop transfer function in the previous lecture, but that's what it is for the system that is shown on the left. And for the right system, where the feedback dynamics and the system dynamics are exchanged, you have k, h of s, and g of s over here. So the factor k is applied to the forward transfer function here. The closed loop transfer function is going to be forward, again, is going to be forward divided by 1 plus product. 1 plus product. Now, both these closed loop transfer functions have the exact same denominator, which means the characteristic equation for both of them is going to be 1 plus k times h of s times g of s equals 0. And we can use this to find out the location of the poles of both these closed loop feedback systems. So once I make the denominator equal to 0, I will try to find out the values of s that make that happen, and those would be my closed loop poles, right? So closed loop poles are actually the roots of the characteristic equation 1 plus k times h of s multiplied by g of s. If I find the roots of that equation, those would be my closed loop poles. So if I can color code this, the closed loop poles would be related to this equation. Yeah. Now, there is also loop poles and zeros. The loop poles and zeros are the poles and zeros of k times g of s times h of s. This is referred to as the loop transfer function. So one is closed loop transfer function, which means that the path is closed and there is some sort of feedback that is connected back to the input side. The other is simply what is the transfer function of the loop. So that is the product of k h of s and g of s in this case, and the same thing happens over here, right? So you have got loop transfer function and closed loop transfer function. The roots of, well, you will have a numerator and denominator. So for using the loop transfer function, you can find the loop poles and zeros, and using the characteristic equation, you can find the poles of the closed loop transfer function. Now, the root locus, which is a sketch, is essentially a plot of the closed loop poles when parameter k is varied from 0 to infinity. So as you increase the parameter k, the closed loop poles of that feedback system are going to move in the S plane. And the root locus is essentially the plot to track that movement of those closed loop poles. So because we are focusing on the closed loop poles, our defining equation for the root locus has to be the characteristic equation, which is 1 plus k times h of s times g of s equals 0. Now we can view this condition boxed up in red as a magnitude value and the angle criteria. So for the magnitude value, we are trying to find out what value of k satisfies that characteristic equation going to 0. So if 1 plus k times h times g is 0, that means k times h of s times g of s equals -1. If I take the magnitude on both sides, I've got k as 1 divided by absolute of h of s times g of s. So that tells me what is that value of k that makes this characteristic equation go to 0. Now, there is also, that's the magnitude evaluation, but we can also evaluate this characteristic equation going to 0 using the angle criteria. And simply that means that k h of s times g of s should be -1, and I can get to -1 with an angle such that angle of k h of s g of s should be negative n times pi, where n is a odd integer, right? So if n is an odd integer, for example, -pi, -3 pi, -5 pi, and so on, you are going to end up with 1 plus k h of s g of s equals 0. So in fact, we can leverage the angle criteria to find the root locus, and that's what we will be doing today. Note, so there can be some confusion about three terms, right? One is closed loop transfer function. The other is open loop transfer function. The other is loop transfer function. Now, closed loop transfer function is pretty straightforward to figure out. Closed loop transfer function is simply forward divided by 1 plus product. That is straightforward. That is your closed loop transfer function. We used that in the previous lecture as well. We derived that in the previous lecture as well, in fact. But what is the difference between loop transfer function and open loop transfer function? Now, the difference is this. The difference is, where are you taking the output? Now, if you are taking the output by cutting off the link over here, then you have the open loop transfer function simply as k h of s. However, if you cut off this link of feedback over here, then your loop transfer function will simply be k h of s multiplied by g of s. So it really depends on where you are chopping off that output. Where are you taking your output? Are you taking your output at y of s, or are you taking your output after the feedback dynamics, right? So that is the difference between open loop and loop transfer function. For this lecture, we will be looking at taking the output over here and not here, which means our loop transfer function and open loop transfer function will be, think of it like this: x going into kh of s going into G of S. And this is your output. Right? So that is going to be our loop transfer function or the open loop transfer function. But that distinction is essentially, made based on where you are taking the output. So open loop transfer function. So the closed loop transfer function is when the loop is closed and you get our forward divided by 1 plus product transfer function. But for open loop transfer function and for loop transfer function, we are considering that to be k times h times g, with the picture that I just showed, like that. Right? Y divided by x is going to be the product of these two systems, the product of the Laplace transform, the transfer functions of these two systems. Next. So we have got an angle criteria where the angle of loop transfer function needs to be an odd multiple of pi. And then I can find out the value of k that makes this happen by evaluating 1 divided by h of s times g of s. So let's take an example over here. We have a closed loop system with negative feedback. And my goal is to sketch the root locus, right? And if the poles are on the root locus, then they have to satisfy the magnitude criteria as well as the angle criteria. So I've got x of s, my h of s is 1 divided by s times s plus 2. And then in the feedback dynamics, I simply have a value, a constant k, right? That I can change from 0 to infinity. So what is the characteristic equation? Characteristic equation is going to be 1 plus k times h of s times g of s. So it's simply 1 plus k h of s equals 0. That's going to be our characteristic equation. Just multiply this with this, right? Forward divided by 1 plus product. 1 plus product goes to 0. That's your characteristic equation. Which means I can substitute for h of s, evaluate the characteristic equation. I've got a quadratic in S. And if the quadratic is in S, I can find the location of the poles. So if I make this 0 and find out the location of the poles, I will get S equals -1 plus or minus square root of 1 minus k. Though that is the location of the poles. And clearly, as I change k, the location of the closed loop poles will change. Right? They may become complex, they may become real, right? But it changes as I change k. So the closed loop poles will move around in the S-plane as I change the value of k from 0 to infinity. That's our goal, to sketch that plot. How do they move, right? So let us start simple. So our goal is to plot the root locations for various values of k here. So in fact, we are trying to do this only for some specific cases. Later on, we will try to make it into a continuous plot, right? So when k equals 0, that is where you want to start. When k equals 0, our s is going to be -1 plus or minus square root of 1, right? So we have got two values here, s as 0 and s as 2 and -2. So those two values for k equals 0, that's your initial point. Where is it initially? Right here and right here, right? The two poles of the two closed loop poles are, one is in the left half plane, so that's stable, but the other is on the j omega axis. So this particular stable system right now, because one pole is on the j omega axis, is going to be marginally stable system right now. Now observe what happens as you increase k, because we want to sweep k from 0 to infinity, and as you're doing that, you want to sketch the new poles, right? Where are those two poles going to move? So if you increase k to 0.5 and substitute it 0.5 over there, you will see that the closed loop poles move to a different value. What happens is, the pole here will move closer, so move to the left, but the pole at -2 will move to the right, indicated by these two green arrows. One is pointing left, one is pointing right. So we can see that as you are increasing the value of k, the two poles are moving towards each other. So that's good, right? Because now this pole has become stable, that pole was already stable, so we would have asymptotically stable system. Good. 0.5 is good. Now, if you go even further and increase it to 1 and 2 and 5, we will see, and then substitute those corresponding values in the closed loop pole locations, you will see that the one pole will move from here, it will come towards the other pole, but at s equals -1, they will break away from the real axis. One pole will go up and become complex, the other pole will go down and also become complex conjugate of the other guy, right? So they are, as long as they are on the real axis, we know that they are overdamped, right? And at this point, when k equals 1, both the poles meet, that's when the system is critically damped. And when you increase k a little bit more, then we get a underdamped stable system, right? So as you can see, we can choose an appropriate value of k in order to get the required damping and required stability, right? But those are, so the green plot that you see with the arrows is what we are after. That's the root locus, right? But because we just did it for some specific values of k, we cannot do that as a general case. We need to establish some rules so that we can sketch this faster, right? So that's what we are going to do. We are going to establish a certain set of rules, and as long as you obey those rules, you will be able to sketch the root locus. So for me, this is almost like a puzzle, right? Like I have to follow these rules and sketch it. So it's almost like a puzzle and fun activity. Let's evaluate the angle criteria. We said that if the characteristic equation goes to 0, which means 1 plus k times h of s times g of s is 0, then the angle criteria says the angle of k times h of s times g of s, for this particular example, we simply have k times h of s, is a odd multiple of pi, minus n times pi, where n is a odd integer. So for this particular example, we had h of s as 1 divided by s plus 2, right? One pole at 0, one pole at -2. Now, if we evaluate the angle criteria, it should be k times h of s equals -n pi, where n is an odd integer. So let's try to evaluate that angle criteria for first column test point, second column test point, and so on. So essentially, what is my first column test point? I'm going to erase this, and I'm going to say this is my first column, the j omega axis. So I'm going to take these specific 5 points and I'm going to evaluate the angle criteria for those test points. So I only have 4 of them, so I'm ignoring the origin here. S equals -2j, -j, j, and j2j, right? For all those values of s, if I substitute that in my k divided by s times s plus 2, note that k does not contribute to the angle, only the s and s plus 2 in the denominator contribute to the angle. And for a given s value in the first test column, say -2j, right? So -2j is where? We are evaluating it for this guy first, right? What happens? Substitute over here, -2j plus 2, evaluate the angle, it comes out to 135 degrees, which is not an odd multiple of pi, right? So the first test point does not obey the angle criteria. And clearly, as you can see here, this point is not on the root locus. It is not on the green lines, right? So everything is satisfying right now. Next, similarly, you substitute negative 1j plus j plus 2j, all the points in that vertical j omega axis. You will see that those points will not satisfy the angle criteria. Hence, those are not going to be on the root locus, which means that no matter what you change k to, it will never be on the j omega axis for these points. It may be for s equals 0. So if you substitute s equals 0, it might come out to be an odd multiple of pi. Next, let us evaluate the second test column. Where is the second test column? If I go back and take a look here, this is my second test column, blue. What is the value of s over here? For this guy, let's see, maybe 0.4 is good. For this guy, what is the value of s? The x-axis is -1 minus 2j, right? And similarly for this guy, the location is s equals -1 plus, minus j, and so on, right? So that is my second test column, and I'm evaluating that for 1, 2, 3, 4, 5 points. I substitute the corresponding values of s in the angle criteria and evaluate the angle. I will see that I get angles 180, 180, -180, -180, -180, odd multiples of pi, right? Negative n pi. When n is 1 or -1, you are getting all of those angles. So that means that these 5 points are satisfying the angle criteria, which means that they should be on the root locus, right? Next, just to close the loop, can I find the value of k for these points? How do I find the value of k here? All I would have to do is use the magnitude criteria. 1 divided by absolute of, what was that? K times, not k, h, simply h of s, right? But you would have to evaluate this at, say for example, you want to use it for this point, right? -1, -2j. So using the magnitude criteria, you can find the value of k for each of those points, and you should, based on our discussion, that point should be k equals 5, right? So this should come out to be, for the given h of s, which is 1 divided by s times s plus 2. What is this going to be? 1 divided by that. So s times s plus 2 evaluated, absolute of this evaluated at s equals -1, -2j should evaluate to 5, right? So you can find out the value of k that makes that happen as well. And you can do that for all the 5 points here. We can do this for the third test column. Nothing will satisfy the angle criteria. We can do this for the fourth test column. Nothing will satisfy the angle criteria. So what is the third test column? That is with the real part of -2, and fourth test column is with the real part is -3, right? So let me just highlight the two test columns here, maybe in pink. So we have got the test column here and test column here, right? So for those values, those are not on the root locus. Let's move on. So now if we plot all these points in the S-plane, we will see that you have got a starting pole here and here. That is when k equals 0. And as you increase k from 0 to infinity, this is going to move this way. All right, let me take green here, and this is going to move this way. This is going to move this way. They are going to meet over here at one point, and then one is going to go up and the other is going to go down, right? So they are going to break away on the real axis at s equals -1. But all these points that I'm highlighting in blue now, they all satisfy the angle criteria. Now we can find the values of s for those points that satisfy the angle criteria by simply doing the simply using the magnitude value of k, right? I just talked about that. So you can take all these 5 points on the second test column, evaluate 1 divided by absolute of h of s g of s, in this case for those specific values of s, 5 of them, and you will see that they evaluate to 5, 2, 1, 2, and 5. So that means when I start over here, k is 0, and when k is 5, I reach all the way up here and up here, right? So this is when it is 5, and in the middle you will have the others, 1 and 2. That movement is not in integer steps, by the way. It is going slowly in a continuous fashion from 0 to infinity. We are just plotting the discrete values. We are not even doing it for all the discrete values. We are skipping over 3 and 4 here. So we are just doing it for 0, 1, 2, and 5. And that will give us some sort of idea about how things are going to move, right? But it doesn't note that when we do this later on for a generic case, we will be evaluating that for all values of k and not just the integer values. Questions so far? There are lots and lots of examples coming your way about how to go about doing this, but for now we are just saying, okay, characteristic equation gives us 2 criteria. One is find the magnitude value of k, and the other is angle criteria. If certain points in the S-plane satisfy the angle criteria, we would know, for a given system, we would know that they would lie on the root locus. And for those points, we can use the magnitude criteria to find the value of k that correspond to those movement in the pole locations. If you're using magnitude criteria, how do you know which columns to test? So we don't use magnitude criteria to do this just because it is too cumbersome to do it using magnitude criteria. First of all, it involves the value k, right? I don't want to have my root locus depend on k. So that is the reason why I used angle criteria, and in angle criteria there is no k, right? If you see this, the magnitude criteria has a k, so I can't use that. That will not give me a proper root locus because it depends on the k, which is why I use the angle criteria, in which the angle is independent of k now, right? So once it is independent of k, then I can find out all the poles that satisfy the angle criteria, but I can use the magnitude criteria to find the value of k for each of those points in the root locus. All right, let's see. Keep moving, and one more. All right. So in this puzzle, we have a lot of rules to follow, and those rules are coming your way now. Root locus sketching rules. And all these rules are based off of the angle criteria. And I just mentioned why we are leveraging the angle criteria and we are not leveraging the magnitude criteria. The magnitude criteria doesn't give us a specific root locus because it has k in it, right? And I don't know k. So I need to leverage the angle criteria so as to make it independent of k. So let's use angle criteria to create a set of sketching rules for more insight into the feedback system behavior. And we are essentially going to be worried about 2 things: stability and damping, right? Those are the 2 things. The root locus starts at 0 when k is 0. So the root locus starts at the poles. Root locus starts at the poles. And as you increase k, it will end at zeros. And we do this for the loop transfer function. As you can see this, the angle criteria, if I go back here, the angle criteria is based on kh of s, g of s, right? So that is the loop transfer function. So what we are doing is we are trying to track the poles and zeros of the loop transfer function and not the closed loop transfer function. But we get to this criteria using the characteristic equations of the characteristic equation of the closed loop transfer function, right? So we start off with the open loop transfer function k times h times g. The root locus is going to start at k equals 0 and it is going to end at k equals infinity, which essentially means the root locus will start at the poles and it will end at the zeros of the loop transfer function. The zeros include the actual zeros that you can sketch on the S-plane, but also include zeros at infinity. So for example, if I go back here, where does this end, right? It is coming here, it is breaking away at -1, but where is it going after that? Well, because there is no zero in this system, what is the system here? 1 divided by s times s plus 2, right? There is no zero here. What does that no zero mean? No zero means the zero is at infinity, right? So as you increase k, this goes to infinity up here and this goes to infinity down there. That means the zeros are at the infinity, right? Sometimes the zeros might appear on the S-plane, which is where they will end as you increase k. But for this particular example, since there was no zero in the system, that meant that zeros were at infinity. That's where the root locus was going. So that's rule number 1. Start at poles and end at zeros of the loop transfer function. Some zeros might be at infinity. The second rule is to find, so there is a big statement here, but in reality, it simply means the root locus alternates along the real axis. No, yes, no, yes, no, yes, and so on. So it's a very simple statement, but all the details are provided here. To find the root locus along the real axis only on the real axis, so only 2 helps you only with respect to the real axis. Start at plus infinity on the S-plane and then move left along the real axis towards minus infinity. So essentially what you're doing is, if I go back here, you are starting all the way to the right here, sketch all the way here, and then moving left on the real axis. And as you are doing that, you are alternating no, yes, no, yes, no, yes for the root locus. So I'm going to sketch, remove all of this, remove this. So you see, so you started here and you started at plus infinity and you started moving left on the real axis. And as you started moving left, you simply said no, yes, no. So this means no root locus here, yes root locus here, no root locus here, right? So you're essentially alternating on the real axis. No, yes, no, yes, no, yes. So every time you see a pole or a zero, you change that no, yes pattern. So the no, yes pattern changes when you have zeros as well as poles, right? But that's essentially what it means. You scan on the real axis from right to left, and as you are moving left, you alternate no, yes for every zero or pole of the loop transfer function. Erase, go back. That's what this means, right? So let us take a look at some examples here. Example 1 has 3 zeros and 3 poles. There is a, so how do I know that I have 3 0? This is open loop transfer function, by the way. Open loop or loop transfer function. So for the loop transfer function, in this case, I have 3 zeros and 3 poles. Let's try to locate those 3 zeros and 3 poles. For the zeros, I've got 1, 2, and 3. And for the poles, I've got 1, 2, and 3. So as you start moving from on the real axis, this is only on the real axis in the S plane. As you start at plus infinity and move left, you alternate. Yes, no, yes, no, yes, no, yes. No here, yes here, no here, yes here, no here, yes here, no here. So yes indicates that there is root locus present there, right? And no means there is no root locus present there. That means that the poles of the loop transfer function will never reach here. They can travel here as you change the value of k from 0 to infinity. So no, yes, no, yes. Clearly, this doesn't help me with the complex region. It just helps me with finding the root locus on the real axis. Another example here for two coincident roots, right? So when you have roots that are coincident, like for example, you have, let's see, yellow, 2 zeros at -1 and 2 poles at 1, right? And if you have that case, you have to think about this as those 2 poles separated by a small section on the real axis. So you would still count that as yes. So you would go no, yes, no, yes, no, and so on. That's how you would deal with two coincident roots. Remember, the root locus starts at poles and ends at zeros based on the rule 1, right? So if it starts with the zeros and ends at, it starts with poles and ends at zeros, there are 2 poles where it starts and there are 2 zeros where it ends, when it is supposed to end. So my guess for the root locus here is it starts here, it breaks away, comes back here, and then ends at the zeros here, right? More about this later on. But I hope you see with this that as you combine the rules of sketching the root locus, you will be able to piece this puzzle together. The next example of root locus on the real axis is when you have 3 coincident poles. When you have 3 coincident poles, all the poles in this case are at -1. You would essentially think of it as 3 poles that are slightly away from each other with some small separation between them. So you would still go no, yes, no, yes, as you do in the previous case. So which means essentially if you combine them all together, this means there is no root locus to the right of -1. There is only root locus to the left of that. All right. Next, let us go here. The next rule is the angles at which the root locus exits or enters multiple poles and zeros. So if it has to start at a pole and end at a zero, right? So it'll have to exit out at some point and it'll have to enter back in on the real axis at some point. Now, for all these examples, that we are assuming that our starting poles and zeros are all real. They could go into the complex, the poles could go into the complex plane, which means that the root locus could be in the complex plane. However, when k is 0, we are assuming that the poles are on the real axis, the zeros are on the real axis, or they could be at infinity, right? So what is the root locus will exit or enter multiple poles or zeros at equal angles, pi over n. So for example, we have here a loop transfer function in which we have 2 poles and then 3 poles and then 4 poles. But all those 4 poles are at -1. right? So you have 2 poles at -1 here, 3 poles at -1 here, and 4 poles at -1 here. So small n is 2, 3, and 4. So the angle at which, in this case, they start at a pole, which means we are only talking about exiting. The root locus is going to exit out of poles, but for zeros it might enter. For these poles, it will exit the real axis at angles pi over 2, pi over 3, pi over 4. So for example, over here, for 2 poles that are coincident, right, it has to exit out, it has to start at a pole. So even though you do not have, so by we know that using the second rule, we had no, yes, no, right? No here, yes in the middle, no here, but in the middle, it had to start at a pole, end at a 0. Where is the 0? No 0. So 0 at infinity, 0 at infinity, right? But it goes outside, out of those poles at a specific angle. And that angle is computed by using pi over n. So it depends on the number of poles. In this case, there are 2 poles, so it is going to exit out at 90 degrees. Over here, 3 poles, right? Now 3 poles mean 3 starting root locus, right? 3 things that are starting at those 3 poles. One goes to the left, but 2 others will exit out the real axis at angles pi over 3. So 60 degrees, and it is going to be symmetric about the real axis. There is always symmetry about the real axis. Next, when k is 4, you have 4 poles here. No, yes, no, yes, no. So that's fine. And every yes that I said in the middle will exit out at pi over 4 degrees. Symmetry about the real axis. All the poles are located at -1. Questions about sketching rule 1, 2, and 3. Starts at poles, ends at 0 as you increase k from 0 to infinity. On the real axis, you alternate no, yes, no, yes. The third rule is if you have multiple poles as zeros, coincident poles and zeros, the root locus will exit or enter the real axis at equal angles pi over n, where n is the number of poles or zeros, depending on exiting and entering respectively, and there is always symmetry about the real axis. Next, we are going to find out some parameters here in order to help with some other rules. The first such parameter that we are going to evaluate is PZE, the pole zero axis. Why does rule 1 work? So rule 1 says my root locus is going to start at k equals 0 and it is going to end at k equal infinity, right? So if I go back here, if you look at this example, we had a characteristic equation. We had some closed loop poles defined by s equals -1 plus or minus square root of 1 minus k, right? And as you tweak this value k, we can change it from 0 to infinity. You can see here, you can validate that the root locus is going to start at the original poles, and then as you increase that, it will come together, break away at certain point, and go towards infinity, zeros at infinity, right? So it's essentially tied to the open loop transfer function and the angle criteria, but it would start at the poles because we are tracking the movement of the poles, right? That's essentially it. And it has to end at the zeros because as you increase k to infinity, eventually what happens to the response? As you have, so think about this in this way. As you have made k equals infinity, you have made the negative feedback infinity, right? That means that you are going to get nothing for the output, right? That's a 0. All right, let's move on here to the next rule. Pole zero excess. PZE. PZE is simply the difference between the number of finite open loop poles and the number of finite open loop zeros. Simple calculation. So consider a open loop or loop transfer function k h of s g of s. We have 1 0 here at -1. So 1 0 and 1 2 3. 3 poles over here. So number of finite poles are 3, number of finite zeros are 1, 3 minus 1 is 2. So the PZE, pole zero excess, for this particular transfer function is 2. And we will use PZE, pole zero excess, to find the number of asymptotes in the system, in the S-plane. An asymptote is a straight line to infinity that a branch of the root locus tends towards. So think of the asymptotes as guiding lines for the root locus, right? And the number of asymptotes that you will have will equal the pole zero excess. So given k h of s g of s, we can quickly find the pole zero excess and hence the number of asymptotes. Let's do that over here. Let's do PZE, an asymptote angle. If you have 2 asymptotes or 3 asymptotes, at what angles are they present? They will be present in the S-plane at asymptote angle AA, which is given by -pi times m, where m is an odd integer, divided by pole zero excess. So we have 3 examples over here for 3 different open loop or loop transfer functions: k divided by s plus 1, k divided by s plus 1 squared, k divided by s plus 1 cubed. So they are poles at -1, 1 pole, 2 poles, and 3 poles at -1, right? So what is going to be the number of, so first you find out PZE, pole zero excess, right? No zeros. So 1 pole here, 2 poles here, 3 poles here. They're all at the same point, but there are 3 of them. Now using PZE, I know number of asymptotes, right? 1 asymptote here, 2 asymptotes here, and 3 asymptotes here. Now I need to find out the angle of the asymptotes with respect to the real axis. And for that, I'm going to evaluate AA, -pi times m divided by PZE, which is 1 in this case. So my asymptote angle is plus pi, which is why this asymptote is at plus pi angle. Next, for the next one, I have got pi over 2 and -pi over 2. And you can see that as you are scanning through multiple odd integers for m, you will only have 2 unique asymptote angles, plus pi over 2 and -pi over 2. And that's all you need to for the AA asymptote angles. Next, when number of poles are 3, then asymptote angles are -pi m divided by 3, and you scan several values of m until several odd integers of m until you see a pattern that repeats. Over here it turns out you will get 60, 180, and 60 plus 180, right? So pi over 3, minus pi over 3, and pi. Those are the 3 angles that so those are essentially straight lines that will guide your root locus. Next, where are the asymptotes located? Well, asymptote location can be obtained by using this. The summation of open loop pole locations minus the summation of open loop zero locations divided by PZE. So if you take this particular example, k times g of s times h of s, suppose we have a specific example, k divided by s times s plus 2 times s plus 4, we know that PZE is going to be 3 poles minus no zeros, so 3. The number of asymptotes are the same as number of poles, so 3 of them. right? So what are those three angles going to be? Plus and minus 60 degrees and 180 degrees. So you can see one line is over here, asymptote, the other is at minus 60, another asymptote, and the other one is over here, right, at 180 degrees. So three asymptote angles. Where is the asymptote location? For that, I need to use this. Pole locations minus zero locations. What are the pole locations? 0, -2, -4. So you've got 0, -2, -4. Divided by, so there are no zero locations, so I don't need to worry about that. Divided by PZE. PZE in this case is 3. So 3 here. Any question?
看不到你的笑，我怎么能睡得着？
All right. As much fun that is, Yingji, you are not muted right now. On another day, I could have done a lot with that, but today I need to cover the material. So let's bring back to this discussion here. Where is the asymptote located? Pole locations minus 0 locations divided by PZE. Pole locations are at 0, -2, -4 divided by PZE. There are no zeros in this case. So the asymptote location comes out to be -2. -2, oh, sorry. So essentially what you're doing is finding out PZE, finding out number of asymptotes, finding out all the asymptote angles, and finding out asymptote locations. Then you would draw straight lines at asymptote locations at angles that are provided by asymptote angles, plus 60 degrees, minus 60 degrees, and 180 degrees, right? The third red line is not given because it's kind of like redundant here, but that's what it is, right? I'm just going to erase that so there's no confusion. Now, what is next? Use rule 1. The root locus is going to start, before we do that, well, let's start with rule 1. Yes, let's start with rule 1. It's going to start at poles and end at zeros, right? There are no zeros in this case, which means all the zeros at which this ends are at infinity. They are going to start here and move right, and start here and move left. Why is that? Because when you use rule 2, you will see that this is no here, yes here, no here, yes here, right? So the only way it can start at these poles and present on the real axis is if it is moving towards each other there. And if it is moving towards each other there, and it has to end at a 0, it has to break away. And break away at a certain point. I don't know what yet. I need to calculate the breakaway point, BAP. I don't know what that is yet. But it will break away on the real axis, and using the asymptotes, those are the straight lines that will guide the root locus, and it'll cross the j omega axis, and it will eventually go to 0 at infinity, over here as well as over here. Now coming to this location, no, yes, no, yes, it will have to start at -4 and move left, and it'll end at a 0 at infinity, right? So I hope you guys are seeing that you can use all these rules and piece this puzzle together to sketch the root locus. The point at which the root locus crosses the j omega axis is called j omega crossing. Are those points useful at all? Why do you think they are useful, the j omega crossing? So the breakaway point can be useful to figure out when does that system become underdamped and critically damped, right? We can find that out using the breakaway point. And what would you find out using the j omega crossings? Would you ever be interested in the j omega crossing? So marginal stability is right, and even worse, if you increase k even further a little bit beyond j omega crossing, you will end up in the right half plane, which means the system is going to be unstable, right? So you want the poles of the loop transfer function to not cross j omega axis. So you essentially, if this is what your root locus is doing, you do not want to increase k to the extent that it becomes unstable, right? Or marginally stable. But this doesn't happen always. So for example, over here, right? No j omega crossing here, no j omega crossing here. There is going to be j omega crossing here. So the j omega crossings are not always there. They may be there sometimes. For example, here it is there. By the way, the breakaway point here is not in the middle. It is not in the center. We need to find that using a different strategy, and we'll come to that in a minute. Next, another example where you have 1, 0. Let's see, where is the 0 here? The 0 is at -4, and there are 3 poles. One is at 0, the other is at -2, and the other is at -6, right? So the zeros and the poles are marked. Now I need to evaluate pole 0 axis. 3 minus 1, 2. Number of asymptotes equals number of pole 0 axis. So 2. Where are those asymptotes located, and what is the asymptote angle? The angle is going to be plus or minus pi divided by 2. We evaluated that earlier for 2 asymptotes. And the asymptote locations is going to be the sum of the locations of the poles minus the 0 locations divided by PZE. So this is PZE. So that's 2. And then you have got 0, minus 2, minus 6. All of that in blue. And then this guy is in yellow, minus the 0. You will evaluate the asymptote location to be -2, which is why your asymptotes that go up and down at angles plus and minus pi over 2 are at -2. Next, no, yes, no, yes. That's how you know where it is on the real axis. Then it has to start at a pole, end at a 0. Over here it's very convenient. Start at a pole, end at a 0. Done. But over here, it starts at a pole, breaks away at a certain BAP point, breakaway point, and then the asymptotes are going to guide it, and then it'll eventually end at 0 at infinity. Let's move on to center of gravity, which essentially means that I am going to have certain root locus move left and certain others move right to balance things out. So if the pole 0 axis is greater than or equal to 2, then the roots that move left balance out those moving right. This essentially gives you an insight and is a good check, right? So if you're sketching the root locus, this is a very quick check that you can do to make sure that your root locus is correct, right? So for example, over here, as you're increasing k, the real pole over here is moving to the right, while the 2 complex conjugate poles are moving left to balance that out. But on this case, on the right, the example on the right, which we had done earlier, as an earlier example, there is one real pole that is moving left, which is balanced by 2 complex poles that are moving right. So in other words, you will not have everything moving in one direction. You will have certain things that are moving left and moving right to balance things out. Next, the question is to find the breakaway points. And we are right now interested in the angles between the entering and exiting loci at breakaway points. So what is the angle at which the root locus breaks away from the breakaway points. The rule is that they are going to be all equal. So it really depends on how many root loci are coming to that breakaway point. So for example, over here, there are 2 root loci entering the breakaway point, and then 2 are exiting the breakaway point. And as you can see, they are all going to happen at equal angles, which is why those 4 lines are at pi over 2 degrees from each other, all at equal angles. This is for the example k divided by s times s plus 2. So 1 0 at 0, 1 pole at 0 and 1 pole at -2 to start off with. And as you increase k, they will come together and exit out. But the angles at which they exit are going to be equal. For the other case, you have 2 starting points that are complex, 2 starting points that are real, and as you increase k, these guys come in, break away at this point and go in equal angles there. So the angles at which you enter and you exit, they are all equal. That's rule number 9 as far as the entering and exiting angles are concerned at breakaway points. Next, break-in points. If I break away between 2 poles, I will break in between 2 zeros. So for example, if I have no, yes, no, yes, no, and I'm starting the root locus at 2 poles, I'm going to have to move left here and right here and left here. I'm going to break away at a certain breakaway point. One pole is going to move in this direction because it has to tend towards a 0. One pole is going to move in this direction because it has to end at another 0. They are going to come back to the real line because they eventually have to end at a 0. That point at which they enter back on the real axis is called the break-in point, and then eventually one of them ends at this 0 and the other ends at that 0. And the way I would describe this system is, it starts at a marginally stable behavior, but as soon as you increase k, the system becomes overdamped. If you increase k even further, the system becomes critically damped. If you increase k even further, the system becomes underdamped. And it stays underdamped as long as the poles are complex. Eventually it goes back to being critically damped, then overdamped, and eventually ends at zeros, right? So the system is moving through a lot of damping criteria over here, right? Starts off with marginally stable, becomes stable, but overdamped, critically damped, underdamped, critically damped here, overdamped here, right? So it's moving through many stages as you increase k. Now, the real point is this, right? I know very easily I can sketch things on the real axis. And very easily I can find out even the breakaway point and break-in point. With a later discussion, you will see that it is pretty straightforward to find out. Break-in point and breakaway point. But the real difficulty is the shape here, right? Is it going this way? Is it going this way? I don't know. So I know that it has to break away here and it has to break in here. However, the shape, when it is complex, is almost, as long as you are sketching this by hand, is going to be an approximate sketch, right? It is not going to be an exact sketch. If we need an exact sketch, the only way to do this is by using MATLAB or some sort of a computer program. On the real axis, you can find things exact, but not in the complex plane. So for example, going back to this, we know that it has to end at 0, but we don't know whether it does this or this or this. I don't know that, right? So it's going to just be a rough approximation there. Next, we need to find out the breakaway point and the break-in point. And for this, I'm going to rely on the characteristic equation, and I'm going to differentiate k with respect to s and equate it to 0. And the reason is this, right? The reason why we can do this is this. As you increase k, suppose you have two poles here and here, right? There are two starting poles, here and here. And you are increasing k now. So for the starting poles, k is 0. And then once you start increasing k, this guy is going to move this way and this guy is going to move this way, right? They are going to move towards each other. And they're going to move towards each other for some time, and then they're eventually going to break away from the real axis. And our goal is to find that breakaway the breakaway point. But I hope you see that if you sketch k versus the real part of S, which is sigma, what are you doing? For this pole, you are increasing k, right? You are increasing k for this pole. What is happening to this? The real part of this is becoming more and more negative, and the real part of this is becoming more and more is positive, right? So it's moving left here and it is moving right here, right? So as you increase k, the real part of both the poles are going to increase here and increase here, right? So that means they are going to eventually break away from the real axis when k versus sigma is at a peak, at a high point. In other words, as k increases, the root locus moves away from the two adjacent poles until it breaks away from the real line. And that means k must be at a maximum value at that point, breakaway point, right? So how do I find that out? Well, you simply differentiate k with respect to s for the given characteristic equation and find the value of s at that breakaway point. So suppose we start off with k, g of s, h of s. That's our loop transfer function. And the example that we are considering is k divided by s times s plus 2. So you have got two poles. One is at 0 and one is at -2. We have marked that. Now, using the magnitude criteria, I know that k equals -1 divided by g times h, which means I can write k as -s squared minus 2s. Sketch that. -2s minus s. It's going to appear like this. Differentiate k with respect to s and equate to 0. You will get s equals -1. That is going to be the point at which it breaks away. Now, it just happens to be right in the middle of 0 and -2, but that's not necessarily the case. Next, let us take a look at a slightly more complex example. And this one will address both the breakaway point as well as the break-in point. So we have open loop transfer function that is given. I've got a 0 at -4, a 0 at -6, two poles, one is at 0, the other one is at -2, right? And I did the rule no yes, no yes. Based on that, I figured out that it has to break away between 0 and -2, and it has to break in between -4 and -6, right? And then I do the solving, so which means I am trying to differentiate k with respect to s and equate it to 0 to find the breakaway and break-in points. So what is k going to be? -1 divided, so what is this? Why is this being written? Because the characteristic equation is 1 plus k h of s g of s equals 0, which implies k h of s g of s has to be -1, right? Which means k equals -1 divided by h of s g of s. That's how we are getting this guy. Because we are after expressing k in terms of s. So you substitute your k, g of s, h of s, rearrange, you can write k as negative s times s plus 2 divided by s plus 4 times s plus 6. You have a polynomial in the numerator, polynomial in the denominator, but you can differentiate this and equate to 0. When you differentiate k with respect to s and equate to 0, you have this big expression that you're trying to equate to 0 here. And then once you do that, you will see that you end up with a quadratic in s, and s equals negative 3 plus or minus square root 3, right? So this gives you a few points. So for example, let's see, s1, the breakaway point, is going to be negative 1.2679. And the only way, so for example, what do I mean by that? If you get a quadratic, you will get two roots of s, right? The two roots of s is negative 3 plus or minus square root 3. So I've got one value between 0 and negative 2, the other value between negative 4 and negative 6. So because I already know that the breakaway point has to be between negative 2 and 0, and break-in point has to be between negative 4 and negative 6, I'm going to assign BAP to negative 1.26 and BIP to negative 4.7. So that has to be done after you have figured out the range of values that could possibly map to BAP and BIP, right? So it has to be between 0 and negative 2. This guy has to be between negative 4, negative 6, right? That's what we said based on the no yes rule. On the real axis. So when you do the differentiation of k with respect to s and equate it to 0, you will get multiple values of s that make that happen. Now, even if you have multiple values of s, you are going to use your previous rules to guide you to pick which one is BAP and which one is BIP. Now, let me ask you guys another question. Can we find out what is the value of k at the breakaway point and the break-in point? Is there a way for us to do that? How do I find out the value of k at breakaway point? So, over here, k is 0. K is 0 here. As you increase k, it comes to the middle and breaks away. Right, magnitude criteria is absolutely right. So k is simply 1 divided by absolute of h of s and g of s. And you evaluate that at s equals BAP, right? So you would use this guy, evaluate that based on this. That's how you would get k. Plug in BAP into h and s. Plug in BAP into 1 divided by, right? Like I'm trying to find out k. So I'm going to use the magnitude criteria to get this. And I can do the same thing for BIP as well. So if I substitute BIP, you will find the k at which the BIP occurs. True or false? K at BIP is greater than k at BAP. True or false? Yes. You're right. True is right. As you are increasing, 0 increases, then you have the break-in point, right? So you have to increase it furthermore to get the break-in. All right, let's move on here. Now, we are going to try to take a look at Routh-Hurwitz criteria, which is essentially a shortcut to find out whether the system is stable or not. Now, what is one way of finding out whether the system is stable or not? You can find out the location of all the poles, right? Find the location of all the poles. So for example, if you have a system closed loop transfer function as P divided by Q, right? So where are the poles? Well, make Q of S go to 0. The value of S that make the denominator goes to 0 are your poles, right? So the poles are going to be the solution to Q of S equals 0. And if I consider Q of S to be an nth order polynomial, I can take that nth order polynomial, equate it to 0. I'm going to get n values, right? I'm going to get n values of, so n poles essentially. Now just imagine doing this for a cubic or a quadratic or a polynomial of 10th order. That is going to take you a long time, right? So to solve a 10th order polynomial is going to require a lot of time and resources, computing resources to do. Instead, we can use this Routh-Hurwitz criteria to essentially talk about whether the system is stable or not by just observing certain characteristics of these coefficients. So we don't have to worry about completely solving Q of S, finding out all the location of the poles, and then saying, oh yeah, all the poles are in the left half plane. It is stable. I don't need to do that. It turns out I can just observe certain properties of these coefficients of the denominator polynomial and get to that conclusion, whether the system is stable or not, right? So that is what Routh-Hurwitz criteria is providing us. It is providing us with a shortcut to finding whether the system is stable or not. For that, I need to construct a table. This is called the Routh-Hurwitz table or RH table. What do I need to do? I need to take in my coefficients. So let me erase this here. How do I form the Routh-Hurwitz table? The first thing I would do is on the left column here, I am going to write decreasing powers of S. I'm going to start off with the highest power that I have in my denominator polynomial, and I'm going to go down all the way to S raised to 0, the constant. Next, I'm going to arrange this table in such a way that I fill in the coefficients of the denominator polynomial in this manner. So for example, I'm going to first start off with a sub n, the coefficient of s sub n. And then as I move right on the topmost row, I'm going to go two coefficients down, two more coefficients down, and so on. So those are over here and so on, right? an minus 2, an minus 4, and so on. The next row is going to be for s raised to n minus 1, 1 power of s less. So here I fill in an minus 1, an minus 3, which is going to be here, an minus 5, and so on. And I keep doing this until I so for these two, I'm set. So for example, let's see, I could take a black line and mark this. So the first two rows in this table, more specifically these values are obtained right from the polynomial itself, right? So that's very straightforward. That is a step that you can do by just looking at the denominator polynomial, which happens to be Q of S in this case, right? So that's very quick. That you can do very, very easily. Once you do that, you are going to have to evaluate subsequent values, b sub n minus 1, b sub n minus 3, b sub n minus 5. In fact, you have to evaluate all the coefficients that are essentially non-zero. The ones that become 0, you can leave them as is. How do I evaluate b sub n minus 1? You have to evaluate the determinant of a sub-matrix. How do I do that? Let's take a look. B sub n minus 1. So I'm trying to evaluate, let's see here, green, b sub n minus 1. What value should I fill here? I need to evaluate negative 1 divided by a sub n minus 1, which is that value there, and the determinant of matrix an, an minus 2, an minus 1, an minus 3. That's how I find out bn minus 1. Next, I need to find bn minus 3. How do I find that? Similar manner, you can see the result over there. So the point is, you would next try to find bn and then cn's and then dn's and so on, as long as you continue building that table until you have the s raised to 0 value by using those determinants, right? So you would essentially find cn minus 1. How do you find cn minus 1? You have negative 1 divided by bn minus 1 here, and then you would evaluate this. So let me do this in blue. For cn minus 1, you would use an minus 1, bn minus 1, an minus 3, bn minus 3. And you would keep building that as you fill out this table. A few examples of this we will take a look at. Now, once you build this entire table, all you have to do is look at the number of sign changes in this particular column. And essentially, if you do not have any sign change in the first column, that means that you have stability. So your system is stable if and only if there is no sign change in the first column. That means that they are all positive or they are all negative. Also, the number of roots in the right half plane is going to equal the number of sign changes in the first column of the table. So if you have 2 sign changes, that means that there are 2 roots in the right half plane, which right away makes your system unstable. So you are essentially looking at the number of sign changes in the first column. That's it. So construct the table and look at the number of sign changes in the first column. That is it. Now, let's come back to dealing with the stability issue, right? You have got this denominator polynomial as an nth order polynomial whose coefficients are known. The system is going to be stable if and only if all the poles of g of s have negative real parts, meaning they lie in the left half plane, left half of the s plane. Recall that poles are essentially the solutions to q of s. So essentially, we are saying, can we find a necessary and sufficient condition that depends only on ak, not on the solution of q of s, but only on the coefficients of that polynomial, so that we don't have to solve for q of s equals 0, which requires a lot of time and computing power, right? So I'm just going to look at those coefficients and be able to comment on the stability. That's the goal of Routh-Hurwitz criteria. So we have talked about the criteria a little bit. Let's just recap that in 4 steps. Step 1 is going to be to consider Q of S with an greater than 0, which means I want this particular value to be greater than 0. What if it is negative? Well, multiply everything by a negative 1, right? I can force that an to be positive. If it is negative, you multiply all of the equation, left hand side and right hand side, by negative 1 in order to complete step number 1. Once you do that, we are going to construct the table of this form. We are going to have row n all the way down to row 0, corresponding to s raised to n all the way to s raised to 0. We have said already that the first 2 columns, the first 2 rows are dependent on the coefficients directly. We can fill that out right away. But the subsequent rows need to be determined by evaluating certain determinants. Now, procedure is provided on the following slides. The step 3 is going to be to count the number of sign changes only in the first column. And if you have no sign change in the first column, that means your system is stable. And in fact, the number of sign changes will be the same as the number of poles in the right half plane. System stability is obtained if and only if AK are greater than 0 and all terms in the first column are greater than 0. Right. So all AK are greater than 0 and all the terms in the first column are greater than 0. No sign change in the first column. Next. By the way, what does this mean? Stability if and only if AK is greater than 0. What does that mean? That means that I need an to be positive, I need an minus 1 to be positive, I need an minus 2 to be positive. I need all the coefficients of that polynomial to be positive. And on top of that, I need the first column over here to have no, all the elements in the first column to be positive as well. Right, so I need to satisfy both of them. Now let's take a look at how do you construct the Routh-Hurwitz table. First, you arrange the coefficients of Q of S in the first 2 rows. The first 2 rows are very straightforward. You build it like this. An goes here. An minus 1 goes here. An minus 2 goes here. And so on. You go up, down, and then alternate, and then you fill out the first 2 rows. That's fine. We also need to talk about how do you find the determinant of a 2 by 2 matrix. We will only have 2 by 2 matrices now. The determinant of a 2 by 2 matrix is product of AD and subtract BC from it, right? We will need this over here. So how do you find Bn minus 1? For Bn minus 1, I'm going to use negative 1 divided by An minus 1 followed by the determinant of this matrix whose elements are highlighted in blue. After Bn minus 1, I will find Bn minus 2, Bn minus 3, which is right here, which is going to be the blue elements again in a determinant expanded over negative 1 divided by An minus 1. And you will keep doing this for Bn minus 1, and then you will continue doing that for Cn minus 1 as well. For Cn minus 1, you have the determinant is elements in the blue, but they still need to get divided by negative 1 divided by Bn minus 1 here. So you would essentially follow these type of rules. You will continue this pattern to evaluate all the elements in the table, essentially the non-zero elements. Once you start seeing zeros, you will simplify very quickly. But after that, you would be essentially looking at the first column of the table to see if there are any sign changes or not. Let's see some examples here. The first example is Q of S is a quadratic. A2 s squared plus A1s plus A0. So over here, row 2 is A2, A0. That's it. And row 1 is A1 and 0. There's no coefficient there. So I just need to evaluate B1 in this case. and B1 based on the formula that were given to you comes out to be A0, right? So by looking at this, we can conclude this second order system is stable if all three denominator coefficients have the same sign. They could all be positive or they could all be negative. If they are all positive, then A0 is positive, A1 is positive, A0 is positive, and even B1 that we evaluated is all positive, which means the first column has no sign change. And if there is no sign change, then we have a stable system. And our A's are positive. If it is negative, then it has to be all negative, right? Like negative 1s squared, negative 2s squared, negative 2s, negative 3, right? And if that is the case, you just multiply everything with the negative 1 to make it into positive. That's fine. So as long as all the coefficients are all positive or all negative, then your second order system is going to be stable. Now this is a generic result, right? So as soon as you see a quadratic with all positive coefficients, you know it's going to be a stable system, which means all the poles are in the left half plane. Next, what if you have a cubic, a third order system for Q of S? In that case, we will evaluate B1 here and C1 here, right? B1 evaluated for this and C1 evaluated to fill in this. And B1 comes out to be, what is B1? B1 evaluates to negative A3, A0 minus A1, A2 divided by A2, right? So you can plug in those values and then evaluate B1, and C1 turns out it is simply A0. Now, using this, we can conclude if A3 is greater than 0, that means the top coefficient is greater than 0 here, which is a necessary and sufficient condition for the third order to be stable. Now we need A2 to be greater than positive, B1 to be positive, and A0 to be positive. So if you have A3 to be greater than 0, this guy is greater than 0, then means for stability, I need A2 to be positive, B1 to be positive, C1 to be positive. Now, using the results that we obtained for B1 and C1, you can break this down into saying B1 is greater than 0, which also means A2, A1 should be greater than A0, A3. And this implies A1 should be greater than 0. So if A3 is greater than 0 and A0 has to be greater than 0 anyway, in order for B1 to be greater than 0, this simply means A1 has to be greater than 0. So you see what happened here. For the third order system, A3 greater than 0, A2 greater than 0, A1 greater than 0, and A0 greater than 0. So if all the coefficients of the third order system are greater than 0, we know that this is going to be a stable system as well. Now we can expand this to a more generic form, right? Like we can apply this to an example here to see whether our system is stable or not. So let's try to work out this Routh-Hurwitz criteria to form an auxiliary equation. The auxiliary equation actually helps in finding where does the root locus cross the j omega axis. And the Routh-Hurwitz criteria helps in determining whether the system is going to be stable or not, right? So let's see. Our example is for the loop transfer function is k g of s and h of s. So we have a system which has 1, 2, 3, 3 poles. One is at 0, one is at -1, one is at -2, right? We have all those 3. And here we are going to use, demonstrate the use of Routh array. Where is the asymptote location? Asymptote location is sum of open loop poles minus sum of open loop zeros divided by PZE. So you do all of that, you find out that it is -1. So at -1, you are going to draw 3 lines, 3 imaginary straight lines, plus 60, minus 60, and 180. Those are the 3 asymptote angles. Now from the characteristic equation, which is 1 plus k g of s h of s equals 0. Substitute the loop transfer function that we have in this example. You will get the characteristic equation as s cubed plus 3s squared plus 2s plus k equals 0. Right? So that's your characteristic equation. Using that, I can build the Routh array or the Routh table. I filled in first. What did I do? I started with s cubed. I went all the way to s power 0 in the leftmost column. Then I entered the coefficients for the first two rows. 1 here, 2 there. Next, 3 there, k there. Right? So far, it was pretty straightforward. Next one was to evaluate this particular coefficient, the coefficient of s. How do I determine that? Well, it would have been -1 divided by 3 and the determinant of 1, 2, 3 and k, right? So that evaluates to -1 divided by 3. Let's see, what do we have here? K minus 6, right? Which evaluates to 6 minus k divided by 3, which is what we have entered over here. And then the last value here is going to simply evaluate to k. So if you take -1 divided by that value and a determinant of this, right? So you see this, how do you evaluate this value? You have -1 divided by 6 minus k divided by 3, right? And then the determinant of 3k 6 minus k divided by 3 and 0, right? So that will come out to be simply just k. That's how we did there. Next, in order for it to be stable, what needs to happen? Well, the first column has to have no sign change, right? So that means k has to be positive. But the real question is, can k be too positive? Well, we can clearly see as you increase k, and the moment it crosses 6, where is it going to be? This is going to be negative, right? The moment this becomes negative, you will have sign change, which means you will have instability. So when k is 6, beyond k is 6, you have an unstable system. At 6, you have a marginally stable system. So if you force this particular row to 0, you will find that k equals 6 is actually where the root locus crosses the j omega axis. Now, what is the value of s at which that happens? You can find that out by building the auxiliary equation. Auxiliary equation can be written using the s squared row, which means I've got 3s squared plus k s raised to 0 equals 0. Solve that quadratic to find the two values of s, plus or minus j square root 2. So those are essentially your two j omega crossings that occur when k equals 6. So this essentially gives you an idea about, all right, when k is 0, I'm here at the original locations, and as I increase k, these guys are going to be stable, but as they increase and move right to balance out this particular pole, they are going to cross j omega axis at certain point. In other words, this particular coefficient is going to become negative at some point, and that value is k equals 6. So what is the range of stability here? Range of stability is this, right? I can have k between 0 and 6. That's my stable region. All right, that's all I have planned for you guys. I'm going to stop the recording here.